So I'm apologizing in advance. I haven't slept last night, so at this point, I'm going to be groping for words, and I'm probably not functioning at that best. So if you find me getting tangled for words, it's just like I apologize. Please, your name tag. I need to know who you are. We're going to be talking about deterministic mechanisms for representing signals. So today we're not talking about learning based. But the problem we're dealing with is going to be that of representing signals. The first and most important step in processing signals is to represent them somehow. And as it turns out, representation is a very fuzzy topic here. Because what does it mean to represent? I know it depends on the perspective from which you look at your data. It's famous poem about these 6 guys from India who tried to, 6 blind men from India who tried to describe an elephant by feeling it. And one thought it was a pillar, the other thought it was a rope, and so on, right? Depending on how you actually sense the signal, how you do it, you're going to get conducted completely different answers. Each one of them is right, and each one of them is also wrong. And so this is going to hold true of representations in general, right? So I've got a collection of pictures on the screen, right? So if I were to ask you, what are these pictures on the screen? And there's somebody else on the other side, can't see the picture, and you have to tell them what pictures are. How would you describe it? What's these pictures? What are these pictures?
That white.
Those are faces, right? So you can actually that's enough. Just saying it through the faces. It's going to tell the other person what these pictures are. And what are these 3 pictures?
Landscape and stuff.
Landscape, a tree. First one is a tree. The second one is trees with a street line with 3 trees, right? What's the third one? A solitary tree in a landscape with blue sky, right? What kind of description is this? These descriptions are good enough for the recipient to get an idea of what you're describing. But what kind of description is it? It's a content-based description. Right? When you begin looking at content-based descriptions, it doesn't scale. There are more images, right? How are you going to begin defining these? There's no clear specified content-based mechanism that I can use to convey the information about my data to the other side. And whatever mechanism I'm using to convey is the representation that I have of a data, right? That actually just so in a generalizable manner. Content-based descriptions don't work. So here's where you could have done one of 2 things. You could have described every single pixel on the image and say pixel 1 is a phone got 227 pixel, 2 is 128. And I could have just told the other person the entire sequence of numbers, the matrix of numbers. It's complete, but it's not informative. If you got a collection of these numbers, you have no idea what these collection of numbers actually mean. On the other hand, content-based descriptions are infeasible in the most generic case. For some subsets of data, for very specific, very restricted classes, maybe you may be able to do it, but it's not a scalable mechanism, right? Same thing with sounds. If I look at a sound recording, that's just a sequence of numbers. But then, if I plot it, it looks like this, right? If I just can tell you about the sequence of numbers I got, 17, 32, 64, 128, 47, does it tell you what the sound was? No, right? I can describe it like so. It looks like a blob. Does that tell you what the sound was? No, right? So, but Alex, thanks for catching those errors in the slides. Was you right?
Wait, what's
You posted on the answer about the optimization. Someone in class also analysis. About the
think it was somebody else.
okay, about the Jacobians and such like that, right? Anyways, So, what is representation? Representation is description, but it's description in a compact form. It must describe the salient characteristics of the system. But what is salient is talking about? Now, here are two images, right? If I look at the pixel-based descriptions of these two images, what do you think the distance between the two images is? It's the maximum possible. Everywhere, every pixel where one image has the value 0, the other has the value 255, and vice versa. On the other hand, are the two images the same?
Yes.
Right? At a completely different level, both represent the same thing. So you get this dichotomy between the actual descriptions and what you're trying to convey. If you're trying to if you're trying to repaint the image, you want the pixel values, right? But you don't necessarily want to be giving them the pixel value. If I had to describe this image in a way which could be painted, I can say this is the black and white image of the character A, where the A is black and the background is white, right? So there was and at the same time, both of them represent the character A. And what kind of representation would tell me that both of them are the same thing in a computable manner? What could I do? Yes.
Could do edge detection.
I could just look at the edges, right? And the sets of edges in both images are going to be identical. And now I know that they can be the same concept. So you want numerical representability, which is why you don't want verbal descriptions. And yet it must allow identification, comparison, storage, and reconstruction. This is what we need from representations of data. And so here's what we're going to do. We're going to define data in terms of basics. We spoke about basics in the linear algebra class. So that's what we're going to use. Now, in all of these images, what's the most common element? In general, what's the most common element in images? It's the background, right? Every image has background. And so, basically large regions of rather featureless shape. So if I had to give you one value to describe a background, what is that value going to be? A background is a uniform sequence of numbers, right? So a background image is just going to be an image of all ones. If my pixel values value in 0. So this would be a background image. Now I have these two data points. If I want to describe it entirely in terms of background, how do I do it? Using whatever new algebraic concepts you can recall. How would I do this? Okay. Pardon me? Projection, right? Exactly. So my background is just a vector. I'm drawing it as an image, but it's just a vector of ones, right? If I unroll the unwrap of the image, it's going to just be a vector of ones. My image is a vector of pixel values. And so I'm going to try to say, when I'm speaking of explaining my image in terms of the background, the only thing I can do is scale it, right? I want to find out how much to scale it by, such that it's the closest to my image in some sense, in some error sense, right? L2 error sense. And so you want to say that my image is going to be some b times a constant. That's the best approximation I can get. And so my image equals b times some constant, right? And how do I find this constant? Pardon me? Okay. So a few of you mumbled it. Can you all say that aloud? Thank you, right? So basically, I'm just saying p times w approximates my image. And so w simply pseudo inverse of b times the image. And now I know how much to scale it by to get my best approximation for the image using based on just the background. Now, is that a good approximation? Here's how the telescope is approximated using just the background. Here's how the face is approximated using just the background. And yet they're different, but can you see faces or telescopes over here? So what will the next thing to do? So what did I do over here? I just captured the most common characteristic of all images, which is the background, and tried to explain the image as much of the image as I possibly could based on this one basis, right? And this is what I got. Then how can I improve on this? How can I improve on this? Yeah. So I'm going to add another basis, right? Again, I'm going to do this in a manner that's kind of computable, right? And so, yeah.
On the previous slide, like, typically, I see what this is calculated, but what is actual, what is that, those gray blocks? Do they represent the most common color? Do they represent the most the average of all?
It just tells you what is the closest approximation to the image. When all you can do is scale the background value. So it gives you some idea that's about it, a uniform background value, right? That's about it. And you can't really get a lot more semantic out of that, right? And then I know that images, background is just constant, but images are not all constant. There's a lot of edges. What is an edge? An edge is a really, really fast change, right? So let me capture the fastest changes in the image. What are the fastest changes in the image? The fastest change in image is where every pixel is exactly the opposite of the adjacent pixel. So there's checkerboard, right? And so I have a second basis. And so now I have two bases, the background and the checkerboard. And now I'm going to try to explain the image as some combination of backgrounds and this checkerboard, right? How would I do that? I can say my background is a bunch of ones, right? And my checkerboard is one where every pixel is exactly the opposite of every other pixel, right? And I'm trying to explain my image as some W1 times basis 1 plus W2 times basis 2. I'm trying to come up with the best approximation of my image in terms of these two bases. But this is B1 and this is B2, right? So how I have to determine the W's which give me the lowest step? How would I do that? You know the answer. Yeah, the answer to everything in the world is pseudorandom, right? Remember this. Anytime I ask you this, call out an answer, you just close your eyes and say pseudo inverse, you'll be right 80% of the time. Right? And so I'm saying I equals B times W. So W is going to be P in B time. Right? And so now I can get my weights and the vector of weights. And now I know how to combine these two bases. So having found that, I found that the approximation I get to this telescope is this. The combination of the best background and the best checkerboard. Does it look like a telescope? So what can I do next? Okay, so what have I missed? I've got the background, I've got the really fast changes, and slow changes, right? So let me add more bases. This guy has the slowest possible change along the x-axis and the slowest possible change along the y-axis. It changes once, right? And both along x-axis and y-axis. The second one has a very slow change along the y-axis. It's about faster change along the x-axis. The third one has steps. There are different forms of checkerboards. Each of them is capturing a different rate of change along the x-axis and y-axis. And you can come up with many combinations of these. As I keep adding more and more, when I throw in up 625 bases, it begins to take some shape. Right? And eventually, how many of these will I need to completely describe my image? I'm going to need as many as there are pixels in the image. Right? That's the dimensionality in the space itself. Now, what was the point of trying to describe the image in terms of these spaces? You wanted to send a compact description that you could share with somebody, right? Now, if you and I both agree that we are going to define the image in terms of bases, these checkerboards, then I can just tell you the weights, and you can reconstruct the image. And if my checkerboards are problems with checkerboards, if I've chosen them properly, then those weights convey some information. There's a lot of background, there's a lot of fast change, there's not a lot of slow change. You get some idea, right? And it will turn out that I don't even need to go all the way to 625 bases. I mean, at about 10,000 bases, thing begins to look like a telescope, which means that instead of sending you a million numbers, which is one value for every pixel of the image, so long as you and I agree upon the basis, I can just send you these 10,000 weights and you can reconstruct the image. So they convey all the information that you need, right? The key is about agreement about that you and I agree on the basis. So there's a first goal. Planning you are on the phone, if it happens, you don't know, but I can want.
Well.
Okay, time's up, guys. Is that first statement true?
Yes.
Second one,
Yes.
third.
No.
Why not?
You could actually get a perfect representation.
So if the maximum number of bases you're going to represent is equal to the number of statements, right? You can't keep adding things beyond that. So these two are true, right? So now what was the point with the checkerboards? The checkerboards are a standard representation. It doesn't matter what image I'm trying to convey, whether it's the face or whether it's the telescope. I can always express that as a weighted combination of these checkerboards. And so I can convey the information about the checkerboard change. On the other hand, when I begin looking at content-based or class-specific descriptions, then if I'm describing faces to you, I'm going to have to describe the type of nose, the type of eye, the person's wearing glasses. The kind of descriptors I sent to you is very specific to the kind of image, right? Because we're talking about descriptors which live in essentially an infinite space. And whereas when you look at these standardized representations, so long as you and I agree on the representation, I can just give you the weights and you can reconstruct them. And so any input, any image over here can be specified as some weighted combination of the checkerboards. Just knowing what the weights are is more than enough for you to reconstruct the image. Now, what about sums? Sum is the blue curve on top is a curve that represents sums. Right? And so they have some length. Although I've drawn it as a continuous curve, it's just simpler than numbers, right? And then I can also represent these in terms of checkerboards. Say the checkerboards are not going to be these square waves. Again, plotting a square wave, but it's basically a sequence of ones and minus ones, the ones and zeros, right? And so I can keep adding these, and these are the sound wave equivalents of square wave equivalent of checkerboards. And I'll use the same approach. I can put all of my bases up in a vector R. My signal is a vector, pseudo inverse will give me the weights, right? And so I can just use I can figure out how these things must be combined to compose my signal. So overall, there's a philosophy over here. And what is the philosophy? We want to identify a set of standard structures, etc. Here, these are our bases. And we're going to express our data as a weighted combination of these bases. And then we want to choose the weights such that the error between the composition that we had in terms of these bases, and the original data is minimized. And typically, the error we will choose is the squared error across all of the samples in your study, right? All of the components of your study. And now, once we've arrived at the standard basis, once you and I agree upon the basis, the set of weights fully specifies the set, right? I just need to convey the set of weights to you, you can reconstruct the set. That's the basic idea behind this. So we just spoke of square waves as bases or checkerboards as bases, but are they the best bases we can use? There are some criteria for good bases. The first and most important criteria is non-redundancy. I could keep giving you the same background basis. Am I giving you more information? I'm not giving you anything more, right? Each basis must capture something that was not captured by any of the previous bases. Mathematically speaking, what does this mean? Please say aloud. Orthogonality, right? You want each basis, each new basis that you have your correction to be, what do you want it to be? Orthogonal, right? To the previous ones. That's what this means is that there's no amount of scaling that I can do to the new basis that explains any bit of the previous basis. And so, when your bases are orthogonal, then you get an added benefit. I don't need to actually pack all of my bases into a matrix and complete a pseudo-inverse of the matrix. I can just figure out the contribution of each of the bases independently by just taking an inner product. Because the bases are orthogonal, right? Whatever you have along the x-axis does not influence what measurement you're going to get along the y-axis because they're orthogonal. So a benefit of having orthogonal bases is that you can compute the individual weights locally. It's typically we will have a basis of length 1. So you can just project your signal on each of the bases and you know how much to just take a dot product and you know exactly what the weight of that base is. This only holds if the bases are orthogonal, right? And so that's one property. You want non-redundancy. The second property you want is compactness, meaning you must be able to express the maximum amount of information about your data using the fewest number of bases. Again, you saw this V1, V2, V3 example in class. And those are kind of compact bases. If I gave you all the V1 and V2 coordinates, even if I forgot to send you the V3 coordinate, reconstruct most of the data, whether it be on that way, right? And so you want that kind of compactness. You want to be able to represent most of the data in the fewest number of pieces. And then thirdly, you need completeness. If I have three-dimensional basis, d-dimensional data, I need to be able to use no more than d bases. If I'm using more than d bases, it means that the bases are explaining one another, right? So, and now, if my bases are orthogonal, and specifically when my bases are on unit length, then there's a very nice property. If I have my matrix P, right? So then here's the property for phi. That I have my matrix P, so this, which is these are my bases. And keep in mind that all of these bases are length 1 and they are orthogonal to one another. Then if I multiply P by P transpose, this is going to be V1 transpose, V2 transpose, right? What is the product going to be? That's going to be the identity matrix. V1 transpose V1 is 1, but V1 transpose V2 and V1 transpose V2. So what is the relationship between V transpose and V?
V transpose of the inverse. V
transpose is the inverse of V, right? So when your bases are orthogonal, you can just transpose the basis matrix. And their unit length. You can just transpose the basis matrix. And they are going to be the inverses of one another. There's a surprising property that falls out of this, which is that if I take my P matrix, right, so what, and if the remember if P transpose is the inverse of P, what is the transpose of P? Inverse of P transpose. B, right? So B transpose B is I, PV transpose is also I, right? What this means is that if you look at this is a matrix of column vectors where every vector is orthogonal to everything else, and every vector is unique. If I transpose this is what it looks like. But if I look at the columns of this new matrix, what will their relationship be? They are also going to be orthogonal, right? If I just pack a bunch of orthogonal, complete set of orthogonal vectors into a matrix, vectors into the matrix, then if I just take the rows are going to be orthogonal to one another, and the rows are also going to be led one, right? That's not something that is obvious. Look at it, it's surprising. If I ask you to prove it, it's going to take a few steps, but then it just falls out because they are inverses of one another, and we know that the transitive property holds for inverses of square matrices, right? It doesn't hold for pseudo inverses, but holds for inverses. So now here's the other thing. If my matrix of vectors, my set of bases is not complete, right? Then is my matrix going to be square? Basis matrix? No, right? If I have a million pixel image and I just give you the background checkerboard and the fast changing checkerboard, there are only two basics. So my matrix is going to be million cross 2. Now it can't be inverted, but I can compute the pseudo, right? What is the pseudo inverse of this? If my vectors are orthogonal, it turns out that the pseudo inverse is also just the transpose, right? This falls out. So it's a very nice property. The pseudo inverse are these cool things. The transposition is the same as computing pseudo inverses for orthogonal matrices where the columns are all orthogonal and are two. So now when I have a basis-based representation, that makes sense to everybody? That makes sense so far? Yes. I'm not going to be jumping around today. If I do, I'll follow this. You are supposed to be enthusiastic. So here's how we are going to use our basis-based representation. I'm going to pack my bases into a matrix. I just want to find the weights with which the bases must be combined to represent my data X. And W is simply going to be the pseudo inverse of my basis matrix times X. Because the pseudo inverse is a magic operation, right? And for orthogonal bases, it's simply going to be the inner product. If my basis vectors are length 1, it's directly the inner product. If the basis vectors are a length that is not 1, I must divide. I must first make the basis vector length by dividing by the length of the basis vector in order to compute the base. Okay, Alex is completed, so here's my clock. What is it? What happened? So, oops, I gave you the answer. What is the answer to the first question? Second one. One is to end the response, right? So if all bases are orthogonal, the weights of the bases for the given vector can be determined individually for each of the bases. And second one is response. Okay. So now we've defined the notion of a basis-based representation. We've defined some properties for ideal bases. But how can a basis really work? So checkerboards are great bases in some sense. Why? Because checkerboards do not explain one another. They're going to be orthogonal to one another. To give you an idea, on average, the amount of black that overlaps white is going to be the same as the amount of overlaps of the same color, black on white. If I put the two checkerboards on top of one another. So when you just take a sample-wise product and sum them up, it's going to go to 0. Right? So one checkerboard, it doesn't matter how much you scale it, will not be able to explain the other checkerboard. So this means that I can compute the contribution of each checkerboard individually. Simply by taking the dot product of the checkerboard image with the original image. And what is that in terms of the dot product? I can just put the checkerboard on top of the image to a pixel-wise product and sum them up, right? And that's going to give me the picture. So it's very convenient. So this holds for checkerboards because one checkerboard does not explain one another. But then checkerboards are not great bases for a different reason. Is there any combination of these checkerboards that can explain the sinusoid?
No, there is, but you probably need like infinite.
It's there. Even if you add, if I have a finite length sequence, there really isn't. But even if I add an infinite length sequence, there is one. Because you can't explain smooth curves with corners. The checkerboards have corners, right? All you can get is somewhat of an approximation. You're never going to be able to exactly explain the curve. Smooth curves are not explained over checkerboards, right? Sharp edges can never be used to explain rounded curves. So that leads us to the actual kind of basis we will use in segments most often, especially for things like sound. Sinusoids. Sinusoids are great bases. Now, sinusoids are orthogonal. If I take two sinusoids of two frequencies, meaning then one can never explain any component of the other. They can explain rounded shapes very nicely because they're fundamentally rounded shapes. But then, for the same reason, the checkerboards cannot explain smooth curves. Sinusoids cannot explain sharp corners, right? So, what sinusoids will we use? You can think of the sinusoid as just a smooth version of a checkerboard. So, if I have a signal, then I have some signal which is going to be something on the sky, what's on the signal, right? I'm drawing this. The signal is actually just a bunch of numbers. I'm just connecting them up for the purpose of visualization, but it's just a sequence of numbers, right? So I have something of this length. Then, if we were using checkerboards, one is just be a constant, right? So the corresponding sinusoid is also going to be a constant. A checkerboard would look like this, right? So the corresponding sinusoid is going to be this. The next checkerboard is going to be like that, correct? So the corresponding sinusoid is going to be this. And so you can have one cycle over the width of the segment, or two cycles over the width of the segment, or three cycles over the width of the segment. What is the maximum number of cycles you can have over the width of the signal? Remember, the signal is not continuous, it's a sequence of numbers, right? So over here, I actually have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 samples. I can have at most 5 cycles. So why is that? When I say that I have a sinusoid of spaces, I don't actually have the skirt. I have these values, which I call the sinusoid, which I'm reading at these 10 positions. So this collection of values is going to be my sinusoid, right? Regardless of the frequency of the sinusoid I use. And so what happens is, I'm just actually taking samples of the sinusoid. So if my sequence has L samples in it, then I can get at most L over 2 cycles. If I go over more than L over 2 cycles, so if I go to L over 2 plus X cycles over the signal, that's indistinguishable from having L over 2 minus X cycles, as you can see in the picture. Because those two will intersect at exactly the points at which you're taking the measure, you're reading the signals. Right? Everybody getting so far?
So saying to which day?
Yeah, essentially, right? So here, for example, I have 20 samples, and I plotted the sinusoid with 9 cycles and 11 cycles. And you can see that at the sample values, the blue points are identical for both of these guys, right? Only have the sinusoid with 11 cycles is just the same as with the 9 as far as we're concerned. Anyway, how do you compose signals from sinusoids? You pack them up in the basis matrix, pseudo-image, no big deal, right? Same as before. And now, what exactly does the sinusoid look like? So if I'm looking at this, there is. So if I'm looking at a sinusoid, right? If I have L values in here, these are L values, then a sinusoid that has one cycle over L values goes through a phase of 2 pi over L values, right? So the nth sample is going to be 2 pi n over L. When n becomes L, you're going to get one full sample, correct? The sinusoid goes through k samples. What's it going to do? So if I have a sinusoid which does this, k times, then what will be? So for the one cycle, it's going to be sine of 2 pi n over L, right? For sinusoid that goes through k cycles, what's it going to do? Yeah, because when n equals L, so you can see that when n equals L, this becomes k, 2 by k, right? Which says that when n equals L, you got k cycles of sinusoid. Each cycle is 2 pi in phase, right? So each column over here, you actually index from 0 to L minus 1 rather than 1 to L. But each column over here is simply the column of these values for different values of k going from 0 to L over 2 in this case, right? Makes sense to everybody, right? And that's my set of sinusoidal bases. Gio, if you want to go and wash your face. Okay? I haven't slept. So, if you go and wash your face, I'll come with you and wash my own face. Okay. So the way I would compute my weights is just pack all of them into a matrix. Pseudo-inverse, no big deal, right? You keep hearing this term pseudo-inverse, and you're going to keep doing so through the rest of the course. So what exactly am I doing? Each sinusoid can actually be treated independently because each sinusoid is orthogonal to every other sinusoid. So now I have this signal for each sinusoid. What I'm actually doing is sort of scaling it until I find the lowest L2 error between the sinusoid and the signal. And that is the amplitude that I have when the sinusoid is at a, the size scale of the sinusoid minimizes the error is going to be the weight of the sinusoid. I'm literally doing this individually for each sinusoid, but that's basically what the pseudo-inverse is doing. Okay? So sinusoids are kind of nice. They're orthogonal to one another. They come to explain smooth curves. They're not sufficient. Why so? Every sign starts at 0. Right? If I have a signal that's not 0 in the first sample, can I ever express it as a composition of sinusoids? Because there's no combination of these guys that's going to give me a non-zero value in the first position. So you can say, okay, fine. What if I use cosines instead of sinusoid? Because after all, a cosine is a value 1 at the first position, right? So now suppose I have a signal that has a value 0 in the first sample, but non-zero elsewhere. Is there any combination of these cosines that could explain that signal? The only way a combination of cosines gives me a 0 in the first position is if all their weights are 0, which means it's going to give you a 0 everywhere. It can't explain anything that's 0 at the edges but non-zero at the middle, right? So neither sines nor cosines are combined. So given this, sorry, guys, give me a minute.
Oh, you just so you have a length of the signal.
Okay. So we have the situation that sines and cosines can get smooth curves, but they're individually incomplete. So how do I deal with that? I can make a sign represent something that is non-zero in the beginning by shifting the sign, right? So now, instead of just using the sign, I'm going to use a shifted sign for each one of the bases. So what we will have here is not sine of 2 pi k n over n plus 2 pi k n over n plus 1, which is the shift of the sign. And so now by allowing these signs to have a certain number of cycles and changing the starting point, I can combine them to construct my signal. Well, yeah. And so now corresponding to each frequency, you will need the weight. You'll also need phase, right? How much it's shifted by. And so how much do the signs shift? So you can actually do this kind of independently. You're still going to be doing this least square split. You're trying to simultaneously find how much, not only are you trying to find how much to scale this sinusoid by, but also how much to shift the sinusoid by for each sinusoid. And for each sinusoid, you're going to try to find the scaling and the shift that minimizes the L2 error between the bases and the signal, right? So everyone with me? And then, if I write this down as my linear algebraic equation, here is my set of bases. Each column is now a shifted sinusoid. Unfortunately, each column also has an internal term of phi. And what are the terms I must estimate? W. And also the phi, right? How much to shift this from? Can I do this linear algebraically? Can I do a pseudo inverse or anything of that kind out here?
Can't get the phi out.
I cannot get the phi out of the basis matrix, right? Phi is a nonlinear. It's inside the basis matrix. And so you cannot actually solve this and find out what the weights are, or solve what for the phases using linear algebra. But then as I promised you, pretty much everything in this course is going to be linear algebra. So that's going to be a trick here, right? And so if I want to make this a linear algebraic operation, what would I want to do? Yeah.
You want to get the phi's out, but the vector W's.
So you want to get the phi's out and put them in the vector with W's. That way, you can still use the pseudo inverse, right? And everyone here? So how can I do that? So this is where we create a cool trick. We go with complex exponentials. How many of you are familiar with wireless formula for
What is this?
complex exponentials? What is it? What is e raised to I theta?
I know what it means, but I look it up.
Anybody else?
What is this?
Cos theta plus I sin theta, where I is square root of -1, right? And so it's up there, so it's great. In general, if I write e raised to j times anything, this times frequency times n, this is going to be cos of frequency times n plus j times sine of frequency times n. So you're actually getting a cosine, you're getting a sine, both of them increase, right? And the two are orthogonal to one another because it's living in a complex space. So the real is actually going to be a cosine, blue, and the imaginary is the sine, the red, right? And so, so now if I do a e raised to, so observe this. I got, regardless of whether I'm using cos or sine, I got j sine when cos of frequency times n, sine of frequency times n on top, right? But then now if I include a phase inside, e raised to frequency times n plus 5, that becomes cos of frequency times n plus 5 plus j times sine of frequency times n plus 5. So I managed to get a phase into the sine and the cosine, right? But then, so I've gone into the complex exponential, but I still have the phase. But then the complex exponential is something very interesting here, right? It's simply going to be the phase factors out. It's e raised to j times frequency times n times e raised to j 5, right? So although in the sine and cosine domain, the phase is inside the sine and the phase is inside the cosine. In the complex exponential domain, it's sort of separated out as a multiplicative, right? And once it separates out as a multiplicative, it means that it still becomes a part of the weight. Make sense? Right? And so we use this trick of going into the complex exponential. If you gather Fourier basics and wonder where on earth these complex exponentials descended on our head from, they descend on our head from the severe fact that the complex exponential allows you to take the phase of the sinusoid, make it a multiplicative, pulls it up, right? And so those are your. So now I'm given any signal, I'm going to have complex exponentials of different frequencies, and I'm going to weight these complex exponentials with different weights. But now the phase is going to be part of the weight. The W is no longer real number. It's going to be some real magnitude plus e raised to j 5, where 5 is how much you must be shifting. Everybody agree? Right. And so complex exponentials, they go next, right? Like sinusoids, a complex exponential of one frequency can never explain one of another frequency. They represent transitions. As a bonus, they're complex. They can even model complex data, right? And real data. And so here is what we're going to do. Now we're going to have complex exponentials of different frequencies. One cycle, and now you can go all the way up to L cycles because they're all going to be different. And so now your basis matrix is going to be a matrix of complex exponential terms. And you have the weights that you'll be multiplying them by. So although the signs repeat after you go beyond L over 2 cycles, right? Cosines repeat after you go over L over 2 cycles. In terms of the complex exponentials, which are different combinations of the sine and cosines, thanks to the location of sine, are going to be unique all the way to L cycles over L samples, right? So you're going to get L bases and corresponding L weights. And so that's what your basis matrix is going to look like, right? And then you have the corresponding weights. But note that the basis matrix no longer includes a phase term because the weights are in the phases are in the weights, and they will be learned as part of the least squares estimate. And so basically, those weights S0 to SL minus 1, uppercase S0 to SL minus 1, they can just be learned by multiplying the signal by the pseudo inverse of the complex exponential matrix. Is it cool? Alex is down, so we're down, right? I'm using it as my clock. Does anybody want to answer that first question? Yeah,
The first one is true.
first one is true. These you one on the second one. Not true. Second one is true. Not true. Not true. And so Tarana, what about the third statement? First problem.
Not true.
Not true. And maybe Yashika, for the second problem, what's the answer? You need L, we said complex exponentials can have L frequencies, right? So this first two are true, the third is not true. If you're using complex exponential bases, you can have L unique complex exponential bases. And the nice thing is that complex exponentials have conjugate symmetry in the sense that e raised to j theta and e raised to minus j theta are basically the same frequency or same value will only be imaginary quotient. Let's split this. So e raised to j theta plus e raised to minus j theta. In one case, you're going to get cos theta plus j sine theta. In the other case, you get cos theta minus j sine theta. If you add up the two, the imaginary quotient will cancel out. And so by adding them, I can actually get both the other. And so complex exponentials with frequencies which are equally spaced from L over 2 are complex conjugates. And so they can be added to compose a pure signal. I'm going to sort of slip over the next few slides before we get into the more interesting things. So what this means is that if I have a complex exponential with frequency L over 2 minus x, and if I have a complex exponential with frequency L over 2 plus x, they are just complex conjugates of one another. Why? We're going to get e raised to j. So if you write this out, it's of g of L over 2 minus x times what is the L over L, right? This is going to be, if I write it down, that's going to be e raised to x power g of M over 2 times N over M. These are things out, right? Times x power g of minus x N over N, right? And similarly, if I write x power g of over 2 plus x times N over N, this is going to be also x for j n over 2 N over x, and then times x for j over x n over x, right? And so these two guys are the same, and these two are complex conjugates of one, right? So you're going to find that if I have L samples in my sequence, then a frequency L over 2 plus x and frequency L over 2 minus x are just complex conjugates of one another. It's a property to use. And so if I say A times complex exponential of frequency L over 2 plus x and the conjugate of A times complex exponential of A plus 0 over 2 minus 6. The two terms are adding a complex conjugates of one another. Their sum is going to be real, right? Which means that now I can actually use these bases to compose real signals. What will happen is that the weights of frequencies equally spaced on either side of the frequency are going to be complex conjugates of one. And so that's how, although we're using complex exponentials, we can actually compose real signals, right? So, is this making sense? And so now look at the bases, right? My bases are these complex exponential. My basis matrix satisfies this complex exponential matrix. My signal, and so I have a set of weights, these uppercase S's. I must multiply the basis matrix by the uppercase S to compose my signal, right? I'm just going to use a shorthand notation. Instead of saying e raised to j2 pi km over L, I'm going to call that the division. Revise that L is going to be the superscript of my W, and K times L is going to be the subscript, right? This divisor L is going to be the subscript, Kn is going to be the superscript. I'm also dividing by 1 over square root of L. Dividing this by 1 over square root of L, so that now each column vector has length 1. I also know that each column vector is orthogonal to every element, right? So now this becomes a orthogonal basis matrix. This matrix over here, which is basically just a bunch of complex exponential terms, where each term has been normalized by the square root of L. This is simply going to be a matrix of unit and orthogonal vectors. What is its transpose? What is its inverse? Transpose. Okay, complex, so it's going to be the Hermitian. It's a transpose and complex conjugate, right? And so here's what I can write. For a real orthonormal matrix, you have XX transpose equals X transpose X equals I. For when they're complex, you transpose it and take the complex conjugate of every term. And that's called the Hermitian. And these two are inverses of one another. Okay. And so here's what I've got. That first matrix to W is my matrix of complex exponential bases, right? Where I have divided every term by 1 over square root of that. Its inverse is simply going to be the Hermitian, where I transpose it and change the sign of the exponent, where I have to take complex conjugate. So this is fine. The W inverse is just WH, right? And so here's what I get. I have my basis matrix times the uppercase S vector to compose the signal shown by lowercase s, right? So which means that this uppercase S is simply going to be the transformation of my complex exponential basis matrix, multiplying my original signal. Making sense? Right? And so this guy to the right is what is commonly known as the Fourier matrix. If you've done Fourier transforms, basically this is the decomposition that you perform. The Fourier matrix, you're using complex exponential bases, but the weights are what you call the Fourier transform. And the Fourier transform values are computed by multiplying your original signal by the Hermitian of your complex exponential basis matrix, which is also a complex exponential basis matrix, right? With a science student. Everybody with me so far? I mean, you can look over the slides. I just sort of conveying this basic arithmetic principle to you. And so these guys here, they're called the Fourier transform or the Fourier representation of the signal. They tell you the components, the frequency components of the signal. How much of each frequency? Okay. So once again, the uppercase S was obtained by multiplying the signal by this yellow matrix. That's the Fourier matrix. And the signal can be obtained by multiplying the SS by the original complex exponential matrix, right? So if you've done your digital signal processing, the equations out, this is basically It's a very simple algebraic operation, often explained with a lot more math than is actually required because it's just basic matrix algebra. Everyone with me so far? And so, what does the basic Fourier matrix look like? If you actually visualize the real portion and the imaginary portion of the Fourier matrix, you get a really beautiful, symmetric, almost fractal-like structure. Because they're capturing all the different kinds of variations in the same slow variations, fast variations, and so on. The boundaries capture the slow variations. As you go further, it captures increasingly fast variations. It's you see the nice pretty structure over here. And so this is what we call the discrete Fourier transform. Now, most of you have probably encountered the fast Fourier transform. The fast Fourier transform, now this discrete Fourier transform is simply a matrix multiplication of your signal by the Fourier matrix. But then as it turns out, the Fourier matrix is very symmetric, as you can see from this picture, right? And so you can exploit this symmetry to make the computation fast. And so in that case, it's going to be the fast Fourier transform, right? So can you shut your laptop there? Thank you. Maybe you should put it in your bag. It's very attractive to the laptop because it always does. So we saw this, we got an idea of how to represent one-dimensional signals. Images are two-dimensional signals, right? And two-dimensional signals have a frequency along x and a frequency along y. For example, if you look at the carpet along this room, it's smooth in this direction, but there are lots of variations in the vertical direction, right? So you can actually have different frequencies along different dimensions. And so here you would need two-dimensional complex exponentials. If you wanted to look at the two-dimensional real and imaginary values of the two-dimensional complex exponentials, they're going to look something like this. That here's something which has no variation along the vertical axis, lots of variation along the horizontal axis, right? This is no variation along the horizontal axis, lots of variation along the vertical axis. This has variation along both horizontal and vertical axes. If you actually plotted it in 3D, it's going to look something like this, with different frequencies along the different axes. And so a signal can be expressed as a linear combination of these guys. And so I can actually plot it because there are frequencies along both the x and the y-axis. The transform will also have two-dimensional representation. With the horizontal axis representing all the horizontal frequencies, the vertical axis representing all the vertical frequencies, and the color over here is shown.
Earlier you said that it's use sinusoidal frequencies as the basis for sound because sound doesn't have edges, it has curves, but pictures don't have curves, they have edges.
Pictures.
So they have like harsh corners and stuff because every picture.
Some of the pictures both have harsh corners. They're once digitized, but this is the sequence of numbers.
But is it not like a series of pixels and therefore like every pixel is a box?
Yeah, but then they're dots. I can connect them up to smooth curve.
Okay.
That's what we use it. But I can connect them up. You're just looking at a sequence of numbers. I could connect them either with a smooth curve or with sharp edges, right? So look at this. I can draw something of this. This is my, if I take one sequence of pixels, it might be something of this kind, correct? And so I can either connect them up like so, or I can kind of connect them up like so. Can I not? Because you're only seeing the numbers.
So the pictures that we're using, we're not interpreting that every individual value is a small pixel box. We're interpreting that they're all
readings of a continuous surface.
Okay.
Right? Because after all, when you see an image, that's just your sensors sampling your continuous image. That's how you view it, right? And so where is all the information? The color tells you the magnitude of each frequency per component. Where's most of the magnitude of the signal. The top left, the low frequencies, 0. So what does this tell us? If you take any image, what is the low frequency component of an image? It's the background, right? Most of your image, regardless of what image you take, is going to be slowly varying. The information bearing content may be in the fast varying portions of the image. But the image itself, I mean, the distinction between a rose and a tree could be in the edges. But regardless of whether you're looking at the picture of a rose or a cat or a tree, it's going to be mostly that. Some slow variation, some slightly less slow variation, and so on. So pretty much every image is going to have a Fourier transform, which looks like this. But most of the information, the energy packed towards wave frequencies along the axis, right? So now, one of the things that happens with real signals, because the Fourier transform for real signals is conjugate symmetric, right? And so there's a mirror image aspect of it is that if your signal, remember the Fourier transform and it's just a transposition, right? The Hermitian. So basically, both the Fourier matrix and the inverse Fourier matrix have exactly the same structure. So we know that if the signal is real, the Fourier coefficients are real symmetric, conjugate symmetric, right? If the signal has conjugate symmetry, the Fourier coefficient will be real. And so if I have a real signal that's symmetric in this manner, the Fourier coefficients are going to be entirely real. We often don't want to deal with complex numbers. So we like symmetric stuff. If I give you a signal, that random signal is not going to be symmetric, right? How can you make it symmetric? Shift. How can I make an arbitrary signal symmetric? I can just take it and reflect it and patch it together. And now I have a symmetric signal, right? And now the Fourier transform of this signal is going to be entirely real, right? And so it turns out that the Fourier transform of signals made symmetric by reflection is what is called a discrete cosine transform. Because in this case, when you actually work out the math, it turns out that the basis matrix is just cosines. And so it will happen. And so similarly, if you are taking images, you have to reflect them along both axes to make them symmetric. There are different ways of reflecting them based on how you deal with the edges. But regardless, if you just make these things symmetric and then take the Fourier transform, that is what is called a discrete cosine transform, which looks like so. And so when we deal with images, we most often just deal with discrete cosine transform. And in fact, your JPEG compression actually looks at 8 cross 8 little blocks of your image and takes the discrete cosine transform of each of these 8 cross 8 blocks. And then when you take the discrete cosine transform, the discrete cosine transform is going to, each of them is going to look like a figure to the out here. And then because these guys here don't seem to have a lot of information, you can throw them away. And so you can just keep a smaller number of things from the top right corner. And so that's all you will store from the discrete cosine transform that each of the 8 cross 8 blocks. And that is enough to reconstruct the image, which is why your JPEG images are so much smaller than actual images, right? So that's basically how we compute your JPEG. Now, one last bit. So these are all what we call deterministic representations. Deterministic representations, they were the basis. Whether you're using a checkerboard, whether you're using science or whether you're using complex dimensional probability, they are chosen by you based on the properties of the basis and nothing to do with the image, right? Now, and we just agree that these bases have some nice properties, and then you and I will agree on the basis. the rates can be only one. So these are the deterministic things. They do not actually consider the data. They have been determined a priori. Now, one last bit. I'm going to talk about spectrograms. It'll take a few minutes, right? How many of you are familiar with tuning forks? Right? So, if I struck a tuning fork of frequency 2000 hertz, what would you hear?
You get a sinusoid wave, like a pure note basically.
You're going to get something which is approximately a 2000 hertz tone, right? If I struck a 2000 hertz tuning fork over here, and I play the 2000 hertz note, what would happen to the sound? Tuning fork?
That's nuts.
It's going to ring with the in resonance, right? And what happens is I increase the amplitude of the tone that I play at this. What will happen to the tuning fork? It's going to vibrate with greater and greater amplitude, right? The higher the amplitude of my 2000 hertz tone, the greater the amplitude with which it vibrates. So now I have a 2000 hertz tuning fork over here, and then out in there somewhere across campus, you have a friend who also has a 2000 hertz tuning fork. And I put a little transducer at the bottom to tell me how much it's vibrating. Convey the signal to a wire and make it vibrate the tuning fork at the other end. Now, if I play 2000 hertz tone at this tuning fork, what will your friend get? Probably here, the 2000 hertz, right? And how does the amplitude of what you hear relates to what you're playing?
The amplitude is reduced.
They're going to be the same thing because this is going to be vibrating according to the amplitude of your tone, right? And because you're capturing the amplitude using your sensor, you're going to be recreating this vibration to the same amplitude at the other end, and they will give the same tone. Does that make sense to everybody? So now suppose I have two tuning forks, one at 1,000 hertz, and another at 2,000 hertz. And we replicated the same thing in your friend's space across campus, right? And I have the sensors on each of these two tuning forks, and I have the signals going out to your friend. And now I play a whistling tone, whistling music, this tuning fork, where I just keep alternating between 1,000 and 2,000 hertz with different amplitudes. What will your friend hear? Guys, that's got to be easy, right? Yes. What's he going to hear? No, I have two tuning forks over here. I have a tuning fork of 1,000 hertz, another 2,000 hertz. Okay. And your friend has the same. And then I'm playing notes, listening. No, going from 1,000 to 2,000 back and forth. What will your friend hear?
Only the 1,000 and 2,000.
That's it. That's all I'm playing. Is going to hear the 1,000 and 2,000 hertz I played again, right? And he's going to basically hear the same thing I played. That makes sense? You guys are all dopey with stuff. So for the next question, I expect some answers. Suppose I put a bank of tuning forks all along. I'm going to put that 30 minutes over. From 1 hertz all the way to 8,000 hertz. 1 hertz to 24, 2 hertz to 24, 3 hertz to 24, all the way to 8,000. Right? And then that's the same. And now I play some music over here. What's your friend going to hear? 8,000 hertz. Please, 1 hertz to 8,000 hertz. Yeah, but what is he going to hear? I'm playing some complex music. The same music. Why? Because this 1 hertz tuning fork is going to resonate in proportion to the 1 hertz component of the signal I play, right? And that is going to be recreated at the other. The 2 hertz tuning fork is going to resonate proportion to the 2 hertz component. That's going to be recreated at the other, right? And so we can actually run this little experiment. And I can have a bank of tuning forks with transducers. I can convey the signals over to my friend. And I can have it activate tuning forks on the other side, and I can play music on the side. You want to get the same music, maybe a little distorted, but basically the same music, right? So did that make sense to everybody? Right? Where was the information about the music there? So here's what I can do. Now, instead of conveying the signals over the wires to your friend, I chop the wires and just read the electrical value off of the signal, off of these 8,000 wires. What am I going to get? 8,000 signals, right? I can store them, and then later sometime I can use those 8,000 signals to excite 8,000 tuning forks. What will happen? I'll play my music right back, right? That's it. Those 3,000 watt, signals that I got. That is my spectrogram. It's doing my frequency decomposition of my signal. Right? It's telling me how the frequencies in my signal change with time. And so that's the exact component we use. And this makes sense because here is basically a bank of tuning forks. So when we process sound, what is a Fourier transform? A Fourier transform is basically emulating a bank of tuning forks. And the amplitude you get is basically capturing the frequency, the amplitude with which the tuning fork itself is oscillating in resonance to any particular that component of the signal. And so this is basically when we parameterize sound, which is something you're going to see in your first homework. You haven't seen it already. We're computing a spectrogram from the signal. What we do is we chop it up into windows. And again, remember, this is what we had, right? I had a bank of tuning forks. And each of them conveyed the signal to my friend on the other side. I chopped it up over here at these signals. And each of them is going to be some signal, right? Which is going to tell me how the amplitude of each of these tuning forks changes with time. That's the spectral content and how it changes with time. But my Fourier transform captures this. So what I will do is chop up my signal into many little segments. And then from each segment, I typically 10 to 16 millisecond segments, 2 to 25 seconds. And from each of those I'm going to compute a Fourier transform. Yeah. And so here's my signal. I'll be computing my Fourier transform one segment at a time. And if I plot them out, I'm actually going to get the spectrogram. This is what you're actually going to see here. I'll stop here. 2 minutes over. This is in the next class. We're going to begin looking at how we can actually learn basics rather than try to go off preconceived notions of what things might be. Nevertheless, very often when we begin reading with data, when you must start off with standard bases of various kinds and use those to come up with representations. There's more on the slides. I will leave it to you guys to go over the slide because my video the way I don't present everything that's on the slides. I expect you to see nevertheless the perspective.